So this is where this is the beginning point for the study of atoms, which are really the particles that make up these elements. And the name comes from the old Greek atomic theory, where people thought those 5 elements I was talking about, that they could be described by 5 regular polygons. That's how those atoms of those elements are different, and whatever. Wrong theory, I won't go deep into it. But in the era of modern physics, we still need to explain what are these atoms made up of. And this is what people were discovering towards the end of the 19th century, getting close to 1800s. So people have discovered, so I guess, let's say, some background material. I guess of the constituents of atom, the first part to be discovered is actually electron. So people discovery of electron by, I'm pretty sure it's by J.J. Thomson, although don't quote me on that because, once again, physicists are terrible historians. But some guy discovered that if you subject atom to some conditions, you can get particles out of it that's not an atom itself. And he measured the properties of the particle that comes out of it. And the electron was discovered in I guess what we could call cathode ray experiments. So cathode ray, everyone here knows what cathodes are? I guess your photoelectric effect kind of mentioned about cathodes. So this is an electric experiment. As in, so you have some evacuated tube. So inside here, it's a vacuum. And what people were doing was, well, I have some electrode, piece of metal that's poking in here. And don't ask me why they were doing this. They were applying voltage to it. So, imagine hooking up batteries to it. Wait, so if I want this to be cathode, that has to be the negative end. So hook up the batteries. And what they would discover is that if you apply high enough voltage, then you would get a beam of particles coming out of here that you could actually see them if you don't make it this quiet vacuum, but put in a little bit of gas, like wait, that's not argon, that's silver. Put in a little bit of argon, then you could actually see these particles. You could collimate them. You could put barriers on it so you get a nice beam, and you could and you can measure their properties. Like by amount of voltage you apply, you could get how much energy do you get, and you can put this device under a magnetic field, and then you would see these beams bend. So so from that you figure out what's the ratio of its mass to charge, that sort of stuff, right? So electron is the first of the parts of the atom to be discovered. That gets people thinking about if these electrons, these particles that are negatively charged from the experiments they've done, if this comes out of an atom, then when you look at an atom, then somehow this atom has electrons inside it. And hydrogen atom is special in that it is the simplest atom. From the experiments they've done, they know it's the lightest atom or lightest element. So if we can come up with a theory that could describe hydrogen atom correctly, then there's a hope of extending that theory to more complicated atoms like helium, lithium, beryllium, boron, carbon, and whatnot. Yeah? So that's why we are looking at specifically stability of the hydrogen atom. So from this discovery of electron and the experiments they have done, they know that this atom must contain inside electrons somewhere, right? All right. So what else should this atom have? Like just taking a guess from the fact that what you know that electron is charged, negatively charged, and what do you know about atom? Like it's some things that just you can kind of guess at from common sense. Properties of atom. Whatever this particle of the element is.
It's neutral overall.
Electrically neutral. I say it's common sense because in your everyday experience, just touching stuff, you know that most of the things are electrically neutral. If atoms make up everything, and if atoms are not electrically neutral, then you're going to have to come up with an explanation why these macroscopic objects are electrically neutral. It's so much easier if you can say this atom is electrically neutral. All right. So you have this thing, particle of the element. And you know that it contains a negative charge inside it, that you can make it pop out. What else must it have? It must have positive charge in there somewhere. So that's really the question people are trying to settle. So you have this atom, which is made up of a positive charge and an negative charge. And it's a question of how could you arrange these charges in a way that that you'd get a stable, stationary, or you'd get a picture that that you'd get something that's stable and has some particular finite size to it. So I guess I don't want to spend too much time on theories that turned out to be correct. One of the, so the same guy who discovered the electron, he had the idea of how this atom could be made. This is the idea he had. So, by the way, this is known experimentally. This is something that can be determined. People actually knew the size of atom. You can get this size from other experiments dealing with, I don't know, viscosity of air or whatever. People knew that atom had a size of approximately 10 to the minus 10 meters. So that's something already known. So what Thomson suggested was, he suggested this plum pudding model. And I have to tell you that this is a nickname that's invented by people who are against this idea. So I don't think Thomson called it plum pudding. But the way the model is described is, well, so in this atom, it has to have this negative charge in it. And from everything that we can tell, this is a kind of elementary particle. It doesn't have any other things inside it. So let's say this is a particle that can be as small as, it's a point particle. So you have a very small point negative particle here. If you wanted to stay stationary in an electrically neutral arrangement, one way to get that to happen is by smearing this positive charge all over this space that the atom is supposed to occupy. So you'd have this positive charge smeared essentially this entire size of the atom.